Okay, guys, in this video, we are going to start talking about bonding theory and get rolling here. So, first thing we go into our bonding theory, the first type of bonding we're going to look at is ionic bonding, okay, and kind of how ionic bonding works. To do that, first we need to know and make sure that we are really solid on is that when you deal with ionic bonding, we're dealing with a metal that's going to be reacting with a non-metal, okay? So you always have to pair those two up for ionic bonding, all right? Now, within that, ionic bonding is where we get this idea of the octet rule, where you need to have 8 electrons around each atom, which would become an ion, in their most outer energy level, or that valence energy level that we've talked about before. So really, we're looking at this idea of how do we get both the metal and the nonmetal to be an S2P6 in terms of their electron configurations, okay? So the way that they do this is there's a transfer, okay? So for ionic bonding, we have a transfer of electrons from one atom to the other. In that case, the transfer causes a cation to form, and it causes an anion to form, okay? Where that cation is our positive ion, this would be the one that's going to be giving up the electron, and this is the one, the anion is the one that's going to be gaining the electron, okay? So if you think about that, when they collide with each other, the one with the higher electronegativity will be the one that gains the electron. The one with the lower electronegativity will be the one that gives it up. It probably also will have a lower ionization energy, to make that happen, okay? When this happens, they start to form what we call crystal lattices, okay? And because we have a positive and a negative, we now have an electrostatic attraction, okay? So the positive side attracts the negative side, or the cation attracts the anion, and that attraction, that attractive electrostatic force is actually the bond, okay? So it's not like they actually tie a rope between the two of each other, something weird like that. It's actually just an attraction force between the positive and negative charge of these two ions now, okay? So as they do this, there's always very specific ratios that can form when ionic compounds bond with each other, okay? It has to be very specific because everybody has to be happy, okay? When I say be happy, I mean they both have to become stable for this to form, okay? So for example, if we take a look at sodium and chlorine, sodium has a single valence electron. If we use the planetary model as our kind of our guide here, chlorine has 7 valence electrons. Well, this ratio is pretty simple because sodium needs to give up 1, chlorine needs to gain 1, so the ratio is going to become 1 to 1. And as they bond, or as they attract to each other, you'll see that this electron gets transferred over, and now sodium loses its outer energy level. It gets smaller, as we would expect, and it now has its 8 valence electrons in the second energy level to be stable, and chlorine fits that 8 one in there to be stable also, okay? So as we look at this, we could give a formula for sodium bonding with chlorine. We call that sodium chloride, or NaCl. Noticing how there's no subscripts here or anything, that indicates it's a 1-to-1 ratio. Same idea down here, except for calcium needs to give up 2 of its electrons. And if chlorine still only wants to gain 1, okay, then in that case, calcium will give 1 of its electrons to a chlorine, 1 of its electrons to another chlorine. So it takes 2 chlorines to make this happen. So for every 1 calcium, we get 2 chlorines. As a result, when this bonds, we get a calcium as a 2+ charge, and we get 2 chlorines now and a -1 charge. And again, we can write that formula up for this, saying it's calcium chloride, and then it's 2, okay? We always want to make sure that we find the right ratio to allow for both parties or both ions to become stable. Now, we know the charges of most of our elements on our periodic table already through our electron configurations and through that pattern we developed. So it shouldn't be too hard for us to just look at 2 elements, for example, aluminum and oxygen, and say, what would that formula be, okay? So if we have aluminum and oxygen, take a minute and think about it. So if you don't know, look up aluminum's charge. So how does it want to ionize? Is it a +1, +2, +3, +4, +8, whatever it is? And what is oxygen's charge? Is it a -1, -2, -3, -4, whatever it is? And then find that ratio between the 2 of them, and from that you should be able to say, oh, it's going to take X amount of these and X amount of those. So do that for a second here, and then pause the video and come back and check out the answer. Okay, so here we go. We know aluminum is a 3+, okay? We know oxygen is a 2-, okay? So as a result, aluminum has to give away 3 electrons, but oxygen is only going to gain 2 electrons, okay? Well, 3 and 2 don't line up. So we need to use 2 aluminums, which will give us 6 electrons to give away. And if we have 6 electrons to give away, it's going to take 3 oxygens to gain all of them, okay? As we take a look at that. So we end up getting a formula of Al2O3 for this. Now, we should probably practice this a little bit because we need to be able to write formulas from elements. If we just say, if they ionic bond, what kind of formula are we going to get, okay? One thing to note, we always put the metal or the cation first in these things. So it's always metal to nonmetal, 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 metal to nonmetal. Notice down here with tin, because tin is one of those metals under the stair-step line, that's a metal that we may not know its charge just by our own background information or looking at the periodic table. If that's ever the case, I will always identify charge ahead of time for you. Now for calcium, I won't, because you should know by looking at the periodic table, calcium is in group 2, so it's a 2+, and so forth, okay? So again, we're gonna let you guys practice this a little bit. So take a minute, pause the video, and just work through each one of these with your partners or by yourself, and solve for what formula you would create for each one of these, okay? Go ahead and pause it. All right, so now that we've paused the video, we're gonna check out our answers, okay? So the way you want to work this out is, well, lithium's a 1+, fluorine's a 1-, so it's a 1-to-1. Magnesium's a 2+, nitrogen's a 3-, okay? So it's going to, if you want to do it mathematically, the least common multiple between the 2 of these is 6. So 2 times 3 gives you 6 for magnesium, and 3 times 2 gives you 6 for nitrogen. So you could do kind of a least common multiple and know the 3 to 2. And then work your way down. So a 3+ and a 1-, so it's going to take 3 of these. Here, okay, one thing to note, it's a 2+ and a 2-, okay? So we don't put 2 and 2 down here because the ratio to balance those charges would still be 1-to-1, okay? And that's what's key for ionic compounds is that you don't just write down the subscripts on this, okay? You don't just say, well, whatever the number here is, I'm going to write it down there. And whatever this number is, I'm going to write it over here. You don't just play switching the charges, like sometimes we call it, because things like this don't do that, all right? So if you have a 2 charge and a 2 charge, they can cancel out with a 1-to-1 ratio. So we show it as a 1-to-1 ratio. Here we have a 3-to-1 ratio, so it's opposite 3-to-1. And again, down here, tin was a 4+, and oxygen's a 2-, okay? So if all we did was write SN2O4, that would be actually an incorrect formula for ionic compounds because you always put it to its lowest ratio. In this case, if tin's a 4+, that means it has to give away 4 electrons. Well, oxygen's a 2-, which means it's going to gain 2 electrons. So as long as we use 2 oxygens, it's 4-to-4, and we have our ratio. So for every 1 tin, we need 2 oxygens, okay? So I always say we do not want to play switch the charge, okay? That may be something you may have learned in a previous class, but for compounds like this and others we're going to see in the future, you'll end up having problems with those, okay? All right, so that's how we build our formulas. Now, these ionic compounds actually form what we call as a crystal lattice, okay? And one reason why we write the formula the way we do and we don't let it pair up into 2s and 4s and that kind of stuff is the fact that actually when ionic compounds form, they form a repeating pattern of their ratio. So sodium chloride is a 1-to-1, so it's 1-to-1, 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 1-to-1. And it doesn't really distinguish, like this is one sodium chloride, here's the next sodium chloride, because this sodium to this chlorine could also be the sodium chloride, okay? So there is no real start or end to a sodium chloride formula, okay? Because it builds these crystalline structures. So these are some different examples of crystalline structures. Here's calcite, sodium chloride, here's another salt one. I don't remember what this one is. But they all form these very geometric crystalline structures. As a result, this is why we don't call ionic compounds molecules, okay? So recall earlier in the year we said that molecules has kind of a specific term to it. Ionic compounds, we would never use the term molecule, okay? The term molecule implies individual packets, or like here's a group of something, and then another group of something, and then another group of something. So we would never say that sodium chloride is a molecule of sodium chloride because sodium chloride actually just forms these crystals, okay? So we could say that sodium chloride is a compound, and it has a crystalline structure, but we would never call it a molecule, okay, because of that crystal lattice. Now, here's a little video of some ionic crystals forming, which I think is kind of cool. That was kind of cool to watch. Just, you can see how they actually kind of grow and spread out as the crystals form. Okay, because of ionic compounds' repeating pattern and because of these crystalline structures they form, we get some unique properties from ionic compounds that we can use to distinguish them from molecules or metallic crystals. Okay, the first one is that ionic compounds are very hard. Okay, so when we have them, they're very hard. Think of all the minerals you maybe have studied in like an earth science class. Those were all ionic compounds. Okay, they're like the rocks of our world, right? So they're very hard. But because they're very hard, they're also very brittle. Okay, and here's why. If you think about it, we have this repeating pattern of plus, minus, plus, minus, plus, minus, plus, minus. So if there's a force that strikes it, the crystal is either going to reject that force and say, nope, you're not enough, beat it, nerd. Okay, and say, nope, I'm not moving because you didn't have enough power behind you. Or if the force is strong enough to shift the crystal, to push these atoms down, all of a sudden you get a positive to positive lining up with a negative to negative, lining up to positive positive. Well, as soon as these things line up, they repel. So that repulsive force between these atoms causes it to crack or to be brittle, okay? So as a result, we don't get a lot of flexibility in our ionic compounds. They're very hard, but they're not very flexible. They're not ductile. They're not malleable, okay? So they shatter or they crack very easily. Now, ionic compounds also have the property that they can conduct electricity in certain situations, okay? So first of all, they have to be a liquid or in solution, all right? So when we say that ionic compounds are liquid, we usually use the term molten because if you heat up an ionic compound hot enough, it turns into this kind of like liquidy phase to it. Ionic compounds have extremely high melting points, so it's really rare that you're going to deal with an ionic compound as a liquid. However, it's very easy to dissolve ionic compounds into solutions. Take sodium chloride, for example, or calcium chloride, or magnesium chloride, or magnesium bromide, or like Epsom salts, or any of those kind of things you work with. They're all very easily and very readily dissolved in water. So as a result, they create solutions really well, okay? And the reason why we need them to be in solution or liquid states is because to conduct electricity, you have to have mobile electrons, okay, or mobile charge, essentially, all right? As a solid, they're fixed in that lattice. So if you put a positive plate and a negative plate on them and touch either side, these negative charges can't slide, these positive charges can't slide, they're locked in place. So you can't get current to flow if you have charge that's locked in place, okay? In fact, ionic solids make good insulators. They're not even good conductors at all. However, you liquefy them or you get them into their molten phase, and what happens then is you actually can get a movement of charge, okay? So these positive ions can slide over here, and these negative ions can slide over here. So as you move charge, the movement of charge, the movement of charged particles allows for the conduction of electricity. 99% of the time, in fact, every time we do this in class this year, it will be ionic compounds in solution, okay? We'll never witness them as liquids because we need to get them like into the hundreds of degrees Celsius to even melt them. So it'll always be ionic compounds in solution that makes that happen, all right? Now, how does ionic compounds dissolve, okay? Molecules and ionic compounds dissolve differently from each other. So when you look at an ionic compound, when it dissolves, it breaks into its separate ions, okay? What we mean by that is here's again our crystal lattice, where we have, again, we're using sodium chloride as our example, but all ionic compounds do this, okay? We have our negative and our positive charges, okay? As water, see these little waters here? As water comes around that and bombards this crystal, what's going to happen is a water molecule is going to come over, grab one of these things and pull it away. Grab another one and pull it away. Grab another one and pull it away. And it pulls it away one ion at a time. In fact, water is really good at doing this. When it does, the negative charged particles will separate by themselves. The positive charged particles will separate by themselves. And the water will actually like arrange themselves around it and almost like surrounding them and like kind of protecting them, okay? But the take home here is ionic compounds split into individual ions when they dissolve, which allows separate positive and negative charge to flow in a solution, which allows for conduction of electricity, okay? Now, last part of this, ionic compounds also have very high melting points, okay? The reason why they do that is because that interlocking strength of the crystal lattice. So that crystal lattice binds together and builds up this kind of like, almost like this like cell like structure where they all help each other and support each other. As a result, as you warm it up, those interlocking charges inside there make it much harder for them to break down and to fall apart. Because when you melt, you need to break down that solid structure, that crystalline structure. So by the binding effect, it makes it really strong, which brings the melting points really, really high, okay? So if we take a look, we have a bunch of compounds here, all right? And we have a bunch of melting points. And take a second here and just, maybe with your partner or by yourself, read through these and pick out the ones that you think have the highest melting and the highest boiling points that could indicate ionic compounds. And then, cross out the ones that, don't look ionic to you. So go ahead and go. All right, so now that we did that, let's take a look. So first thing, let's cross out the ones that don't look ionic, okay? So ethanol, melting point was negative, okay? Ammonia, melting point was negative, okay? Hydrogen chloride, melting point was negative. Methane, melting point is negative. The only substance up here that's even close to the ionic compounds, even close, is water. And water doesn't have a metal in it, first of all. So that should help you out. And even then, water has a melting point of 0, okay? So even though water was higher than the rest, it's still not an ionic compound. If we take a look at what's left, these are our ionic compounds. Cesium bromide, 600 degrees to melt it, over 1,000 to boil it, okay? Look at this, magnesium oxide. It takes almost 3,000 degrees Celsius to melt it. That's crazy hot. Remember, water boils at 100, okay? I mean, this is what? How many thousands of times more than that, okay? Sodium chloride, table salt, it takes 800 degrees to melt this thing, okay? Yeah, we don't do that in a normal lab setting. It's just way too hot, all right? That's why whenever we want ionic compounds to be more of a solution, we just dissolve them in water. It's way easier, okay? So yeah, super high melting points for our ionic compounds, all right? Now, that ends this here. Our next segment is metallic bonding and how metallic bonding works. So we'll end it here. Thank you.